Hi, folks. This is our second lesson in a series about volume. So, this second lesson talks about how to find volumes of solids using what we call the disk method. So, in this type of volume problem, we think about a region in a plane that's being revolved or rotated about a line in the plane, and this gives us a solid which is called a solid of revolution. So that's the kind of solid that we're going to be finding the volume of, and this type of solid will always have a cross section which is a circle or a circular disk. And let me show you what I mean by taking this example 1. So in this example, the region bounded by the graph of y equals rad x and the x-axis, please add those words in there. So we are looking at the graph of rad x, the x-axis, and then we're between x equals 0 and x equals 4. So we're taking this region, so let's picture the region. That's step 1, is sketch the region that's being rotated. So in this problem, the region looks like something like this. Here's rad x, and I am going between x equals 0, that's there, and x equals 4, that's here. So I have those two vertical lines, and then I have rad x and the x-axis down here. So my region is this yellow region right here. And what we're doing is we're taking this region and rotating it about the x-axis. So you will notice that one of the boundaries of the region, which is the x-axis, is also what we call the axis of rotation, AOR, or axis of revolution, sometimes we say. So then you have to imagine this line, this black line here, coming out through the page and over back into the page. So the way I like to draw this is to reflect this graph down here, make just a reflection, and then we're going to imagine the rotation. It's coming out and going back in, coming out and going back in, and that keeps happening until this x equals 4 line. That's where we stop our region, right? X equals 0 to x equals 4. And so each of these cross sections now is a disk of thickness dx. So the thickness of these disks is dx. And the area of the cross section is going to be the area of this circle. That's going to depend on the x that I'm at. You can see that the bigger the x is, the bigger that area is going to be. And you can also see that the radius of each of these disks is the y high, which is rad x, minus the y low. The y low is right here on the axis of revolution, right? It's so the axis of revolution is the line y is equal to 0. And the distance between that and the rad x graph is just rad x. That's going to be my radius. So how we do these problems is we sketch the region and picture the solid. That's what I did in terms of drawing that revolution. Then we find the radius. So I already showed you the radius. The radius of any disk is this distance from here to here, from here to here. So the y at the top of that is just rad x. It's a vertical line. So it's the y value on top minus the y value on the bottom. In other words, just rad x is the radius of the every disk. So you can see the bigger the x, the bigger the radius. And I'll just write it like this just to remind you it's going to be like a y high minus a y low because it's a vertical line. Then we are going to write the cross-section area, which is pi r squared. So it's the radius is rad x. So if I square that, then I just get pi x. And then step 5 will be to set up the integral. The integral will be a dx integral because these disks are being stacked side to side. And the limits on the integral will be x values. Those will be the 0 and the 4. And the a of x is what's going to go in here. So pi x goes in there. And then step 6 will be to do the integral. So that's pi x squared over 2. We're going from 0 to 4. So pi 4 squared over 2 minus 0 squared over 2 is going to end up giving me 8 pi. So 8 pi is going to be the exact exact volume of that particular solid. And this method is called the disk method of finding the volume of a solid. Let's try another example here. So the region bounded by y equals x cubed, y equals 1, and x is equal to 0. This means the y-axis. This region is rotated about the line y is equal to 1. So this is again a horizontal axis of revolution. Okay, and we are finding the volume of the solid. So step 1 is the sketch and picturing the region. That's really step 2, the picturing of the region. Okay, so the sketch is we are looking at y equals x cubed. So that will be something like this, 1, 1, and then 2, 8. So that's this graph of x cubed. And then we have the line y is equal to 1. So that's a horizontal line. That would be this line, y equals 1. And the y-axis, x is equal to 0, right? We already said that is this line, x is equal to 0. So these are my 3 boundaries here. So the region is this little sliver that's caught in between here, this yellow piece. That's my region. And if I'm going to spin that around the line y equals 1, then this is my axis of revolution right here, this same line. And so I'll just reflect it onto the other side. This is the way I picture these. Just reflect that graph there like a mirror image. And then imagine connecting those with circles like that, connecting the top and the bottom graph with circles. And these circles are going to be your disks. Okay, so these have now thickness dx. They're stacked side to side. So their thickness is a little piece of the x-axis, dx. There's going to be an infinite number of them. That's why we do an integral. And then the area is going to be the area of the face of each circle. And the radius, which is going to be our next step, will be from here to here, from the, or we can even think of it, it'd be better to think of it down here to here, right? So this, you're on the axis of revolution, that y value, which is going to be 1, minus the y value down here, right? So we're going to find that our radius for this problem, that's step 2, radius is going to be equal to the y high would be the line y equals 1 and y low. So y high is like here, y high, and y low is down here. So y low is on the x cubed graph, y high is on the y equals 1 graph. So I can just say the radius is going to be 1 minus x cubed, and now the this is actually step 3. Step 4 will be finding the area. So the area will be just pi radius squared. So let me just say that it's a of x, because as you change your x values for the different positions, right, these different disks are going to have different areas, and those areas are going to be pi times the radius squared. And so then step 5, the integral. The integral now will gather up all of these disk volumes, and we'll start the integral here at x is equal to 0, and we'll end here at x is equal to 1, because that's the intersection points. If you're wondering, how do I know that? It's because, you know, when I say x cubed, we really need to set in general, we need to set these two equations equal and find the intersection point, which is at x is equal to 1. And then the other end of this is over here, where x is equal to 0. So those will be my limits of integration. So volume will be equal to the integral from 0 to 1, pi 1 minus x cubed, the quantity squared dx. We should be able to do this integral without math 9. So please remember to FOIL this out and don't just distribute that power, because that's not how those work. So we get this right here, 1 minus 2x cubed plus x to the 6th dx. Pull the pi out, and then antiderivative is x minus 1/2 x to the 4th plus x to the 7th over 7, going from 0 to 1. And so the bottom will all be 0, and the top is 1 minus 1/2 plus 1/7. And that, if we put it over a common denominator of 14, gives us pi times 14 minus 7 plus 2 over 14, which is 9 pi over 14. So that is the volume of that particular solid. And in general, to find the volume of a solid obtained by revolving around a horizontal axis, notice that in both of those examples we were revolving around a horizontal axis. We use the disk method and this formula, which is the volume of the solid is pi. You can pull the pi out. Integral from a to b of the radius function squared dx. Notice that if we're stacked horizontally, we integrate dx, and this function is in terms of x when we're stacked horizontally. Let's now talk about vertically stacked disks. Okay, so example 3, the region bounded by y equals x cubed, y equals 8, and x equals 0 is rotated about the y-axis. Find the volume of the resulting solid. So right away I'm noticing that the axis of revolution, the AOR, is vertical. We already know the equation of the y-axis is x is equal to 0. Let's sketch the region and picture the solid. So those would be the same, similar to the last problem in the sense that it's y equals x cubed. So we've got this graph. However, now the second boundary is y is equal to 8. So you know that if you set x cubed equal to 8, then x would be equal to 2. So we know that this point right here, this point of intersection is 2, 8. And our region is the region trapped between this line and this x cubed and this x equals 0 or y-axis. So here's our region. I'll just shade it in here. And we're revolving it around that yellow line, because that yellow line, the y-axis, is the vertical axis of revolution. So we're going to just, draw the solid, and for that you just reflect it on the other side. So just draw a mirror image on the other side, and then you just connect the two ends of the boundaries of the thing by circles like that. Okay, so here the boundaries of the solid like this. Okay, so now you can see that here the thickness of the solid is this way. That's like the thickness of the disk, is like that. It's a little piece of y. So dy means a little piece of y. And then the area of each disk is going to be this area. And it's going to be a function of y. We're going to find the radius, which is going to be this radius. We're going to find this radius of each disk. Okay. So this radius, now I'm on to my step 3, is going to be equal to an x right minus an x left. And when I think about it, x right is on this blue graph, and x left is this yellow line. So the yellow line is the line y equals 0, so x left is 0. The blue graph is y equals x cubed, which means x equals y to the 1/3. So my radius is going to be y to the 1/3 minus 0, or y to the 1/3. Step 4 is to think about the area of each disk. It's going to be a function of y, right? And the way to think about that is as you go up this champagne glass, the disks are getting bigger. So that means the area of the disks must be a function of y. A of y is going to be pi times the radius squared. So that can be written as pi times y to the 2/3. Step 5, set up the volume integral. The volume integral is like you're literally filling that champagne glass from the bottom, which is down here, all the way to the top, from y is equal to 0 up until y is equal to 8. We're filling it with discs of champagne. So we get integral from 0 to 8 pi y to the 2/3 dy. So here, notice the structure of this is a of y dy, and each a of y dy is the volume of one of these disks. And they are, of course, like infinitely thin, right? Because their thickness is only dy. So we have an infinite number. You add them all up, you get an integral. So step 6 is simply to do that integral, and we'll just find the antiderivative. So pi comes out. 2/3 plus 1 is 5/3. Flip that thing. 3/5 y to the 5/3 is the AD. Go from 0 to 8. And then we have, let's see, 3 pi over 5. That's a constant out front. 8 to the 5/3 minus 0 to the 5/3. Hopefully you remember this. You've seen it a few times now. 8 to the 5/3, you do it by going 8 to the 1/3 to the 5, and that's 32. So 3 pi over 5 times 32 minus 0, which is 96 pi over 5. Let me double check. Yep, that's the right answer. So there you go, a champagne glass example of a vertical axis of revolution. Okay, the last problem here, another vertical axis of revolution, and this is a calculator active problem. So the region bounded by y equals x squared over 4, y equals 0, and these x boundaries, 0 and 6, is rotated by about the line x equals 6. So x equals 6, this is a vertical axis of revolution. Okay, so let us picture the region and the solid. That's steps 1 and 2. Okay, so we can draw our axes and just think about this graph. This will be a parabola squished down. So you can plot some points and realize when x is equal to 4, if y is equal to x squared divided by 4, that's 16 divided by 4, or 4. When x is equal to 6, it's 36 divided by 4, or 9. So that should give us a couple of nice convenient points on this graph. And then we've got a parabola going like this, and we're going from this line x equals 0, right, all the way until x equals 6, so until here. Those were the vertical boundaries. And then what else did we have? Y equals 0. Oh, so interesting, we are actually between the graph and the x-axis. This is the x-axis. So the region is right here. It's this region in here. Okay, and we are rotating it around this line x equals 6. So to make the other side of this, we want to just reflect this on the other side. And so I'd go 6 over 1, 2, 3, 4, 5, 6, and then over here I'd have a point something like this. I mean, it's not a perfect picture, but we'll try to do reasonably well. and bring this graph something like this would be my reflection. And then the spinning is happening like this over and around. The line, the whole region, it's like a piece of cardboard, like coming out of the plane and just going all the way around. So we would have these kind of discs like this. And notice that they are vertically stacked on. So it's like kind of like a circus tent or something that is made up of these discs like this, okay, or a party hat, sort of like a party hat. And those are our discs. We can see that the thickness of the disc is a little bit of the y-axis. Now, the radius of the disc goes from here to here, right? So we've got x right, which will be this, x is equal to 6, and x left will come from this equation, y is equal to x squared over 4. So that must mean x is equal to the square root of 4y. And you can write that as 2 square roots of y, okay? So I think we're on to step 3, which is writing the radius equation. So the radius is x right minus x left, so that is 6 minus 2 square roots of y. The area of a disk is pi radius squared, and the volume is going to be the integral. Remember, we're integrating from the bottom to the top of this solid. So we're going from y is equal to 0 at the bottom, that's here, all the way up here to y is equal to 9. Okay, and how did I figure that point out? That's by realizing that that's the place where we're on the parabola and on the line x equals 6. So if I'm on the parabola, it's x squared over 4, but I'm also at this place, x equals 6, because I'm on this line too. So that means the y value there must be 36 divided by 4, or 9. So that's why I know that this point right here is 6, 9. And that's how high I need to go to get to the top of my solid. So 9 at the top, and then just put this integrand in here. Remember, please remember not to just distribute the 2 because it doesn't get distributed. So we'll go off here to just make sure we know that 6 minus 2 rad y times 6 minus 2 rad y is 36 minus 24 rad y plus 4y. So that's my integrand. And so I'm going to write it this way, 4y minus 24y to the 1/2 plus 36 dy, and antiderivative becomes 2y squared minus 1/2 plus 1 is 3/2. So I got to do 2/3 times 24, which is 16 y to the 3/2 plus 36y, going from 0 to 9. And this is going to be 2 times 81 minus 16 times, remember 9 to the 3/2 is 9 to the 1/2 cubed, so that is 27. So I've got here, wow, 16 times 27 plus 36 times 9. So this is 162 minus 16 times 27, which is 432 plus 36 times 9, which is 324. 324 plus 162. You can use a calculator on this. I just don't have one handy, so I need to just do it this way. This is coming out to be, I think, 54 pi. And I believe that is the right answer. You can also practice doing math 9 on this, and a decimal answer for this would be 169.6460. So you need to know how to do these both with math 9 and a simple integral like this. You should be able to do by, manually finding the antiderivative as well. So to conclude, we have learned that the disk method with vertically stacked disks works Also, and to find the volume of a solid obtained by revolving around a vertical axis. So when the axis of revolution is a vertical line, that's when we're going to use the vertical stacking, because the disks are going to be, like that champagne glass. And in that case, the dy is the thickness of each disk, and the pi r squared is the area of each disk. If we keep the pi inside, then we can, say that's the area. But of course, when we do the integral, we pull it out. These here are y values, which are representing the top and the bottom of the solid. So I hope you enjoyed that lesson. These are kind of fun, some very cool shapes. And I will talk to you soon to teach you the last in our volume series in the next lesson.